The final lesson of Chapter 9, Differential Equations, is logistic differential equations. Now, this is something that is unique to BC that we didn't cover in AP. And a logistic differential equation is one where the rate of change is proportional to the population. And the difference between 1 and the ratio of the population to the carrying capacity. What the heck? This is, carrying capacity is something that I think you talk about in biology. So, logistic differential equation helps us figure out the rate at which populations change when a carrying capacity is involved. Now, here are two forms of logistic differential equations. The rate is proportional to the population and 1 minus the ratio of the population to the carrying capacity. So that's the rate at which the population is going to be changing, depending on what this constant of proportionality is and what the carrying capacity is. Now, a different form of that equation is this right here. And it's difficult for me to tell you which form you're going to be using. It all depends on how the problem is presented. Now, let's do an example. The solution to the logistic differential equation will take the form, before we do an example, we don't have to separate and integrate a logistic differential equation. The solution, we want to find the population at any time. The population at any time is the carrying capacity divided by 1 plus a e to the negative k times t. Well, you know t stands for time. You know k is this value right here, if you're using that form of the equation, or maybe it's this value right here if you're using this form of the equation. You know what E is? What the heck is A? Well, A is found by taking the carrying capacity minus the initial population divided by the initial population. This has got some complexity to it. So, with that in mind, nice that we don't have to separate and integrate. Nice that they have given us a formula for the solution for the population at any time. Nice that they've given us a formula to figure out what A is. And is this some formula that we need, or are these two formulas that we need to remember for the AP exam? Well, there will be at least one question using differential equations on the AP exam. And there's a good possibility it could be a free response question, in which case many points will depend upon your knowledge of logistic differential equations. So let's say that we actually do know this solution right here. We remember that for the AP exam. And we remember this method of figuring out the value of A. Let's answer example 1 here. Write the solution to the differential equation dp dt equals, and use it to find the population at a time of 40 and the population at a time of 80. Well, okay. Now I look at this. And does this look like differential equation of form 1 or a differential equation that is of this form over here? The PDT equals 0.08p 1 minus p over 1,000. I think it kind of looks like this form right here. And if that is indeed the case, which it is, we've got K times P. I think K equals 0.08. One minus P over M. What do you suppose that number is? I think that is M. I think that is the carrying capacity. So if I know these different forms for the logistic differential equation, then when I'm given the rate at which the population is changing with respect to time, I can figure out what K is and I can figure out what P is. And now I'm going to use those things using these equations over here. I'm going to say that the population at any time is equal to the carrying capacity, which in our case is 1,000, divided by 1 plus, I got to figure out what A is, but I remember this equation right here. A is equal to the carrying capacity, 1,000, minus the initial population, which they told us is 100, divided by the initial population, which is 100. Well, these are pretty nice numbers. I think we can probably do this in our head. You get 900 over 100. I think A is 9. E to the opposite of K. We said K was 0.08. So E to the negative 0.08 times T. That is the population depending on what the value of T is. So now you can press pause shortly. You can put a 40 in for the T and see what you get for the population. Why don't you do that now and then resume. And let's see what we come up with. I get that the population at a time of 40 was equal to 731.604. Now, I don't think that we're going to, if we're talking about populations, I don't think we're going to have partials. So I think we'd say the population was 731. If we put an 80 in there, you go ahead, put an 80 in there and see what you get, and then resume playing this and see if you agree with my answer. Of 985-ish. Sure, there's a decimal that comes after it, but we're only going to deal with populations being whole numbers. All right, now let's use this solution to figure out when the population is going to be 900. Well, that's a challenge. I'm going to say that 900 is equal to 1,000. 1 plus 9 e to the negative 0.08 times t. And the only unknown is t. So that's nice. How are we going to figure that out? Well, I think we're probably going to cross multiply. And we're going to have 900, 1 plus 9, e to the negative 0.08 t, equaling, and if I put this over 1 and cross multiply that way, we have 1,000. If I divide by 900, I think 1,000 divided by 900 is 1.1 repeating. And I think if I subtract 1 from each side, all right, well, this is an interesting quest for the value of t. Now, you know what? If the population's 900, that falls in between 731 and 985. So I better get an answer that's somewhere between 40 and 80. If I don't, well, then I got a problem. I would think I would divide by 9. And I think this is 0.0, 1, 2, 3, 4, 5, 6, 7, and it keeps going and going and going. But you've got that number on your calculator and use the entire thing. I think I would go from exponential form to logarithmic form, or natural log both sides, whichever one you're most comfortable with. They accomplish the same thing. On and on and on. Use all those digits.
To those staff members that are in the building, please disregard the Raptor.
And if we now divide by negative 0.08, you let me know what you get. I think that we're going to get T is 54.903. Now this is a time, and so therefore I think that to have decimal places here is fine. And whatever the units for time were, I don't even know if that was even given to us. Okay. So that's how I would use this logarithmic differential equation. Now let's go to one more example. Again, we have the two forms of the logistic differential equation, and it's something that right before the AP exam, I'm going to try to cram into my head if there's any room left in it. This guy, I'm going to have to remember this. I'm going to have to remember this. Now, if it's for a single multiple choice question, it's a lot of stuff to cram into my head for one problem. But if it is that free response question, well, then it may be worth several points and therefore worth the effort. Now, in example 2, we got to figure out what K is and the carrying capacity. For the population that's represented by this differential equation. Well, again, I'm presented with a differential equation, and is this of the form 1 or form 2 of this logistic differential equation? Well, I don't see the 1 minus. And so therefore, I'm thinking that this is situation 2. Let's see. Let's see now. I think that K over M, let's see. How am I going to do this? If I took this times M, I think I would get K times P minus, now I have to distribute this here as well. And I would have K over M P squared. That's almost like a third form of this logistic differential equation. So, 0.04 P minus 0.1234 P squared. That is what K times P minus K over M P squared is equal to. Well, this is 0.04 times P, so K times P is the same as 0.04 times P. I think we got K is 0.04. Now we got to find the carrying capacity. Well, this is the coefficient on P squared. 0.0004 is the coefficient on P squared. That's equal to K over M times P squared. So, dividing each side by P squared, those are gone. 0.0004 equals, now we know K is 0.04 over M. And if you want to cross multiply and solve for M, however you want to solve for M, whatever method from algebra you remember, I would have cross multiplied. And divided each side by 0.0004. I think you get M, and double check my work, but I think you get M is 100. Now, one other thing. There isn't another example, is there? No. One other thing that comes up. Now, logistic differential equations for the populations that behave, that have a carrying capacity, oftentimes look like this. Here's a population at any time. Here's the amount of time that goes by. And they usually start at a population here, and then they start to rise, and then they level off. They level off up here at a value very close to that carrying capacity. That's as large a population as that habitat can support. Now, you can see this was kind of concave up, and then it became concave down. There's a point of inflection in here. And the question often comes up, when is the rate of change the largest? Okay, when was this moment when the rate of change is the largest? And I'll tell you something, it often, no, I'm going to tell you that it always happens when the population is half of the carrying capacity. So if you're asked, let's say the carrying capacity, like in this last thing, was 100. If they say, what's the population when the rate of change is the largest? You would say 50. That's the population when the rate of change is the largest. If they say, at what time is the rate of change the largest? Well, then, like we did back here, we would have to solve the differential equation for the time. But we'd have to start with a population that is half of the carrying capacity. So 50 would be equal to a carrying capacity of 100 divided by 1 plus, now we weren't given enough information in this most recent example to figure out what A is. E to the negative, and I think we figured out that K was 0.04 times T. We just weren't told what the initial population was, so we don't have enough information to find it. But if we have to find the time at which this rate is the largest, we at least will know what the population when the rate is the largest is. And now we'll be given enough information to figure out what T is. So just realize the greatest rate of change, steepest slope of this thing, and this is always the shape of a graph for a logistic situation. The rate is always the largest when the population reaches half of the carrying capacity. Okay, assignment in Schoology, go to it.